So we're on to section 5.3 and we're talking about friction. Now with friction, it's important to get a good intuitive idea of what's going on, which you do already have, right? You know how friction works, even if you never really thought about it. You understand that if I take an object like this and I try and push it this way, then if I take a heavier object, so I'm just finding what I can find, so I've got a dice and a stapler, so a dice is a lighter object. If I push it like this, then there's some sort of resistance to me pushing. I have to actually push a certain with a certain force to get this moving. If I take a heavier object and I push it, then I'm going to have to push harder to get the object moving. Okay, I can put a force on this object. I'm pushing there on the stapler a little bit, but I'm not pushing hard enough to actually make the stapler move. If I push a bit harder, then the stapler starts moving. So all of these things are things that we know from everyday life and from experience. We just need to sort of classify that knowledge a little bit, and then we need to turn it into the equations that we're going to use. So first of all, we've introduced that idea that if we have a heavier object, then it tends to be harder to move. Okay, now it gets a bit more complicated than that, but that's the important feature of the objects for the moment. If you have something that's pushing down harder, then the friction force is bigger, because when I start pushing, I have to push harder. What is it that I'm overcoming? So let's imagine this here. There's an object and it's sitting on the table. If I push this way, then what's pushing back to the right? There's nothing at all, right? At the moment, there's nothing on this diagram. So in real life, why is it that I have to push with any sort of force? Why couldn't I just put the tiniest, lightest force and this thing starts accelerating to the left? Well, the reason is because there is friction. Okay, the friction is the thing that's stopping it moving, and that therefore must be pushing back against me. Okay, so if I push to the left, the friction pushes to the right. On the other hand, if I push to the right, the friction doesn't go, oh well, for this stapler I've decided to push to the right, so when I push to the right, the friction doesn't join in and help me. The friction opposes me. So if I push to the right, then the friction pushes back to the left. Okay, so that's the first thing, is that the friction is opposing. It's not trying to do anything, right? It's a natural force. It doesn't have sort of agency, but we can think of it as though it's trying to stop the movement, or if something is moving, it's trying to slow the thing down. And the other thing is this idea that if I have a more massive object, if I have a heavier object, then it's harder to get it going, so I have to push a bit harder. Now the way to think about that is that actually we're not going to say that the friction is related to the weight force. So here's the object here, here's the weight force pushing down. I'm not going to say friction is related to the weight force, I'm going to say friction is related to the reaction force. Okay, now obviously if there's nothing else going on, the reaction and the weight are equal to each other. But imagine this, here's my dice, and this time, it's quite easy to get this dice moving. It's not very heavy, it's not very massive. But what if I push down on the dice? Then now what's happened is that the weight force and my pushing down are acting downwards. So I've got an object like this, but that has increased the frictional forces, right? If I now push sideways on the dice, it's harder to get that dice moving. But what is pushing this way? Well, there's no force that I've added that's pushing that way. All I'm doing is adding a force pushing downwards. So adding that force pushing downwards increases the friction, right? Because the thing that's opposing this sideways force here, the thing that's opposing this force and stopping this dice accelerating off in that direction, is this frictional force here. That is the only force that's going on. Now, rather than saying the friction is related to all the downward forces, when I push down on that, if you look vertically, there's no acceleration going on. So the weight and my downward force have to now be equal to R. So what we do is we say that friction is related to R, okay? Now, again, I'm pushing on, I've got this dice and I can be pushing on it or I can be not pushing on it. If I push very, very slightly, if I just put a tiny little force, so this force here, if I make it a tiny little force here, then the dice doesn't move, okay? Now, that means that the friction force that's pushing back against it must exactly balance out the force that I'm pushing with. So if I push a little bit harder, then again, in this case, I'm pushing a little bit harder. You're going to have to trust me here. You can try it yourself. But if I put a tiny little force, there's no movement. If I push a little bit harder, there's still no movement. If I push hard enough, then I can start my dice moving. Okay? So that means that when the force that I'm putting on here isn't so big that it makes this thing move, the friction must be exactly matching it because it's maintaining the equilibrium. The forces to the left must be equal to the forces to the right. So that means that friction, if this thing isn't moving, there's no friction because there's nothing pushing left or right, so there's no friction to push back. If I push a little bit, friction matches the force that I'm putting in. So if I push a little bit to the side, friction will exactly match it. If I push hard enough, friction gives up. So friction must increase to a maximum. And also we have that friction is related to the reaction force. Okay, and the way that we think of that is if I'm pushing down on top of the dice, it's harder to get it moving, and the reason it's harder to get it moving is because my downward force increases the reaction force as well. So the way we express that with our equations is we say that friction is less than or equal to mu times the reaction force. So this is a letter mu if you've not met that one before, and this mu is called the coefficient of friction. Coefficient of friction. Okay, now we say less than or equal to because the maximum F max is equal to mu r. So when we say, well, if I push hard enough, this dice starts moving, whether I'm pushing down on it or whether I'm not pushing down on it, there's a certain force that I need to put in to make the dice start moving. There's a maximum force the friction can get to, and it turns out that once an object is moving, it doesn't exceed that maximum force. So friction will increase up to mu r. Once we get to mu r, then the friction starts moving. So what is mu? It's this thing called the coefficient of friction. And the other thing that we've not talked about, I suppose, is it depends on the surface. Now, we tend to say in the questions that the surface has a coefficient of friction of mu. Actually, the coefficient of friction is going to be, is more carefully, if we think about it, is to do with the contact between the two surfaces involved. So between the surface of this dice and the surface of the page, there is a coefficient of friction. Between the bottom of this stapler and the surface of the page, there's a different coefficient of friction. If I were to take the bottom of this stapler and sort of polish it, then that would reduce the coefficient of friction, wouldn't it? Or if I were to put some oil on here, then there would be a different coefficient of friction. It'd be easier to move. If I were to take the bottom of the stapler and cover it with sandpaper, that would increase the coefficient of friction. So rough surfaces have a higher coefficient of friction. Lower surfaces have a lower coefficient of friction. Okay. Now, how big can a coefficient of friction be? Well, the lowest value we can have for a coefficient of friction would be 0. Now, when I say the lowest value, practically we can't really have a coefficient of 0. That would be a perfectly smooth surface. But we use that as a modelling assumption sometimes, don't we? If we have a perfectly smooth surface, the coefficient of friction is 0. Now, if you look at this, the coefficient of friction is 0, which means the maximum possible friction is 0 times r. So the maximum possible friction is 0. That means there is no friction, okay? Now, practically, you might have some particularly smooth surfaces where you have a very, very low coefficient of friction, but we can't actually have literally no coefficient. We can't literally have a coefficient of friction of 0. But in the questions, we could do. Usually in the questions, they don't disguise it like that. They will just say it's a smooth surface. Smooth surface would mean a coefficient of friction of 0, which means there is no friction. Now, coefficient of friction basically goes between 0 and 1. You want to think about a coefficient of friction as going up to 1. I've actually just had to double check this because I don't know if there's any sort of theoretical reason. It turns out there isn't a theoretical reason, there isn't even a practical reason. The coefficient of friction sometimes can be bigger than 1, but mostly it's helpful for these questions to think about it on a range that's between 0 and 1. So basically a coefficient of friction 0.9 is a very, very high coefficient of friction. Coefficient of friction of 0.1 is not very high, okay? Usually in the mechanics A-level questions, we have coefficients of friction about 0.2 or 0.3, something like that. Sometimes we might have slightly higher ones. But having just double-checked it to make sure I'm not telling you anything that's not true, apparently there are sometimes coefficients of friction greater than 1, which would mean, you know, a very, very rough surface indeed, okay? So, we have the following facts then about friction. These are the important ideas. The friction, which direction does it go in? Well, it tries to stop or slow down the movement. So if I'm pushing that way, the friction acts that way. If I'm pushing that way, the friction acts that way. It doesn't have to be any particular size. It starts off at 0 if there's no force acting left and right, there's no friction. If I increase the force, then the friction increases, and it increases up to a maximum of mu r. And so for all static problems, mu times r is the maximum, and friction could be anything up to mu r. When it's moving, when your object is moving, now we haven't quite said this, when it's moving, it turns out that friction doesn't increase or decrease. If you're accelerating or decrease or decelerating, it doesn't matter. If you're staying at a constant speed, it doesn't matter. Friction is as big as it can get. So friction does really get to a maximum amount and then just give up and say, right, this is as good as I can do. That's the force you've got to overcome. And that maximum is mu times r. And we get a lot of questions which say this object is on the point of slipping, or it's in limiting equilibrium. And what that means is, practically what it means in our equations is mu times r is what the friction is, but the forces are still balancing out. So it means that we're pushing right on the edge of it actually moving. That means the friction is a maximum, and he's just managing to stop it moving. Friction can't get any bigger. Any tiny extra little bit of force would make the thing slip. In the equations, that means we can put friction equal to mu r, but we still use all the things we have for static objects. So the forces are still balancing out left and right and up and down, okay? Now those are the ideas with friction. So let's get on and have a look at how it affects our questions. And the sort of diagrams we're going to start drawing here are very familiar diagrams, but now we have to put some friction in there. And how's that going to affect them? Well, like this. So in this first question, I'm looking at example 8 on page 100. We've got a particle of a mass 5 kilograms. So that's 5g pushing down, and it's pulled along a rough horizontal surface by a horizontal force of magnitude 20. So we've got a 20 Newton force pushing. It doesn't say in the question that it's pushing to the right, but we may as well put it on pushing to the right. If it is pushing to the right, then the friction must be pushing back to the left. It is moving, so the friction is the maximum friction. So if there's 5g pushing down, there's a reaction force pushing up. This friction must be equal to mu times the reaction, whatever mu happens to be. Now, the next sentence says the coefficient of friction is 0.2. So we'll put that over here to use later, okay? So it is moving, doesn't matter that it's accelerating, particularly friction is mu times r, okay? Now, if it is accelerating, then we have an acceleration, and it doesn't tell us in the question what that acceleration is. And this is another one of those situations where all we can do is apply the equations. Once we've applied the equations, we'll see how those manage to solve the questions that we're looking for. So before you start the question, in the example, they look at the forces vertically, then they look at the forces horizontally. Before we start the question, I'm not sure which one of those equations is going to get me what I want, but it doesn't matter. I'm going to write both of them down and then look at it. Okay, that's a technique we're used to from the last couple of chapters. So I'm going to think vertically. I'm going to think, is it accelerating? Well, vertically, it's not accelerating upwards or downwards. It's staying on the table. So I'm going to resolve forces, and I get r equals 5g, and I'll call that equation number 1. Horizontally, I'm going to apply F equals ma. I'm not going to balance the forces out because horizontally this thing is accelerating. It must be accelerating this way, by the way, because 20 newtons is pushing that way, friction is pushing backwards. It can't be going this way because the only thing pushing back that way is friction, and the friction can't push harder than the force that I'm pushing with. There's no situation where I push this stapler that way and it starts accelerating in that direction. So we're using that sort of, intuition and real life knowledge to tell us that it must be accelerating this way. So 20 minus mu r equals mass, which is 5, times acceleration, which is a. And there's equation number 2. So we know that mu is 2, so I suppose we can put that in. 20 minus, mu is 0.2. 0.2 r equals 5a, so I'll call this one equation 2. So what have we got? Well, we've got an equation with an r in it, we've got an equation with an r and an a in it. Can you see the familiar sort of setup? We look vertically, we look horizontally, we get 2 equations, maybe from balancing the forces out, maybe from F equals ma. Once we've got those 2 equations, there will be some unknowns in the equations. In this case, it's r and a, which is fairly usual, but another question, they might not tell us what mu is and ask us to work out mu, but they will tell us r, for example, or they'll tell us a, but they won't tell us mu and they won't tell us r, or they won't tell us what the force is. It doesn't matter, they're going to miss out one of these forces, or one of these numbers, or two of these numbers. From those two equations we can always find them. So r equals 5g, substitute that into here, sub equation 1 into equation 2, and we get 20 minus 0.2 times 5g equals 5a, and then let's divide the whole thing through by 5, would give us 4 minus 0.2g equals a. And that would give us the acceleration there, okay? Now, that is the idea, but again, we use the same idea over and over again, and we use it so many times that it's worth us doing another couple of examples. If you're confident, I would suggest skipping straight past example 9. I'll do it for people that want to see it. Example 10 is a slightly different thing where we're going to go and put things on an inclined plane again, so that one's probably worth watching. I won't do the whole of example 9, but let's just get into the habit so that you can start to see the pattern a little bit here. We've got a block of 5 kilograms, so there's 5g newtons pushing down. It's on rough horizontal ground, and the coefficient of friction between the block and the ground is 0.4, so mu equals 0.4. A horizontal force P is applied to the block. It doesn't tell us in which direction, but we're going to put it on this way. I like to start my forces at the object and move them away from it, so I'm not putting it on over here as they do in the textbook, I'm putting it on over here. Find the magnitude of the frictional force acting on the block and the acceleration of the block when the magnitude of P is the following things. So I'm just going to look at the first eventuality here. This is 10 newtons. And the reaction force is pushing upwards, so the friction force is pushing back this way. And I'm just going to put it on as F for the moment. In fact, you know what, I'll not even do the 10 newtons, I'll just call that P. So what do we have? Looking vertically, we're going to resolve the forces because there's no acceleration going on. So R equals 5g. Horizontally, now we don't know if this is accelerating or not, do we? What we know is that P minus F is the resultant force. Now if that resultant force is positive, there's an acceleration. If that resultant force is negative, well, sorry, it can't be negative. If P and F cancel each other out, then there's not an acceleration. So what I know is that F max equals 0.4, that's mu, times R, which is 5g. So F max is 19.6 newtons. So P minus F, well, if we have the situation where P equals 10, then P minus F, well, in that case, friction can be as big as 10. So the friction force would also be 10 to balance out the P, because I'm not pushing hard enough to overcome the friction. If P was 19.6, then friction can get as high as 19.6. So again, the friction is going to be 19.6, and we're not going to have any acceleration, we're not going to have any movement. Friction would be as big as it needs to be to balance out the force. And then the other example, 30 newtons. If P is 30 newtons, then friction gets as big as 19.6 and then can't get any bigger. So it would be 30 take away 19.6 would equal mass times acceleration. And we can work out the acceleration. What is it actually asking us to work out for? Find the magnitude of the frictional force. Well, in that case, the frictional force would be 19.6 because the force I'm pushing with is more than 19.6 and it can't go any higher than that. The next stage would then be to apply F equals ma. And I have this equation here. And I know the mass is 5. So I can find the acceleration if I want to. And we already know what they are, don't we? Okay, so there's example 9. Example 10, and we're back to this from earlier in the chapter. Hopefully this is a familiar situation to you by now. I've got an object sitting on a plane, I've got a reaction force here, and I've got a weight force here. In this case it's a 2 kilogram mass, so it's 2g pushing downwards. Now this, if I put this object on this plane and it was a smooth plane, would start accelerating downwards. In real life, why is it true that if I have an inclined plane like this and I put something on it, sorry, you can't see that, but if I'm lifting this paper up here, then that dice isn't moving. Why is it not moving? Well, because there is some friction that's stopping it moving. If I lift it up just a little bit more, then it starts moving. And we should be able to see before long why that is the case, that if you increase the angle, well, perhaps you can see already, if you increase the angle, then, then we increase this angle here. And if this angle here increases, this weight has a bigger component going down the plane. So that weight, that component down the plane will overcome the friction force pushing back up. Perhaps we're getting ahead of ourselves there. We have this situation, an R and a 2G. Why is this thing not sliding? Because there is friction. So friction is pushing this way, stopping the thing sliding. And in this question, it tells us this thing is accelerating with 1 meter per second, 1 meter per second down the plane. So therefore it's moving. So therefore this friction force is a maximum and is equal to mu R. Okay. Now once I've got this situation, hopefully this is fairly familiar. We're going to resolve our forces perpendicular to the plane, and I'm going to get that R is equal to 2G cos 30. This force here is equal to this component of the force here. I'm going to look parallel to the plane. I'm going to apply F equals ma. Down the plane I've got 2G sine 30. That is this component of the force. Up the plane I've got mu times r, and that equals the mass, which is 2, times the acceleration, which is a. There's equation 1, there's equation 2, and now it's asking us in this case to find the coefficient of friction. It's asking us to find mu, but it tells us the acceleration a. Okay, so I can just change that acceleration into a 1. If we look at these two equations, there's an r in this equation, I know everything else, so I've got r. If I take r and substitute that into here, then in this equation I know that bit, I know what g is, I can work out sine 30 and I can times it by 2. I don't know what mu is, I do know what r is, so I can substitute that in. So there's only one unknown in this equation. So it might be a bit of a nasty looking equation, but we can solve it. Can you see again that I'm not looking for what they're asking for? I'm not looking at which bit to do first. I'm just looking at this situation, put all the forces in the diagram, ask the question, what's happening in this direction? Well, in this direction it's not accelerating, so balance the forces out. What's happening in this direction? And there are only two options, either it's accelerating, or it's, well, I suppose it could be moving at a constant speed now, couldn't it? But it's either it's in equilibrium or it's not. If it's not in equilibrium, then forces this way take away forces that way is our resultant force. Maybe it's, maybe we're pushing it up the plane, so forces this way take away forces this way. But we get the resultant force equals mass times acceleration. Once I've got those two, then I can ask myself, well, do I know the acceleration? Do I know the coefficient of friction? Can I put any other information into these equations? But these are really my main two equations. Once I've got those two, I'll be able to work out whatever I need from there. One last little note, of course, if I'm pushing this thing up the plane, the friction is going to be pushing back down the plane. So if I suddenly said, well, this situation changes, somebody comes along with a rope and starts pulling up the plane, that mu r there wouldn't stay there. It would turn around and start acting against pulling up the plane. Okay, so if I'm pulling it up the plane with a certain acceleration now, friction suddenly turns around and acts down the plane. And that's a trick they pull off, and part A, this thing's sliding down the plane. Part B, they say, oh, well, now somebody puts a force in. And the mistake that people make a lot of the time in an exam is to put an extra force in instead of completely redrawing the force diagram, because actually everything would change because the friction would change on them. Okay. Worth a lot of practice that. They slowly increase in difficulty, those questions, and get quite hard by the end. We'll see a lot more of them in chapter 7, but for now, that's the end of chapter 5. Good luck.